Okay, so limits at infinity. You have seen this before, but I felt like we probably need to revisit it. And you can see kind of some guidelines on page 201 if you want to. When we look at this first little guy, and there's a couple of ways that you can approach some of this, but most of it you can just sort of common sense sort of think through. Infinity, I'm thinking gigantic numbers, right? If we have 3 over a gigantic number, what kind of fraction is that going to make? What's happening with that fraction? It's getting tinier and tinier and tinier and tinier. It's getting closer and closer to 0. So I really have here a 4 plus a 0, which in this case, so the limit is it's approaching 4 is what's happening. If you wanted to, you could have created common denominators, put them together so that you've got a rational function that looks kind of like this, like it's a big old fraction with a function over a function. And whenever you do that, you could use, do you guys remember I passed out some notes a while back? It's got a table on it and talks about, oh, if the degree of the top is bigger than the bottom, then here's where the horizontal asymptote, or if the degrees are the same, you do leading coefficient. Remember that whole mess? I personally don't have that memorized every time. I always kind of have to go back and refresh myself, and I'm assuming you are probably in the same boat. So I think for most of you, what's going to be best is to kind of use today's sort of think it through kind of method. You know what I'm saying? I think that's probably going to be best. I'm missing a stack. Here we go. Anyway, so there's that one. Let's look at the next one, number 2. Now, here is something to kind of think about. We're shoving in gigantic numbers into these guys, and you're going, well, this one has a -1 and this one has a +2. Think about it. If you're Bill Gates and you've got an infinite amount of money, and you lose $1, are you going to spend much time looking for that dollar? Probably not. In the grand scheme of things, that dollar doesn't matter at all. So let's just pretend like those guys aren't there because they really don't matter. And let's put in super large number. So 2 times super large number over 3 times super large number. You're going to keep winding up with that sort of ratio over and over and over. And can't you also just sort of, now that we've gotten rid of these guys on the end, you can cancel out your x's. You can't do that any other time, by the way. And you get 2/3. Leading coefficient over leading coefficient. That's from that table.
How are you able to just get rid of it?
Well, because we're looking for a limit. We're not looking for an actual answer. So in like most situations, this is one of those posters up there where you kill a kitten. You know what I'm talking about? Every time you do this, a kitten dies. This is not really that situation, because if you shove in huge infinitely large numbers right here, this 1 and this 2 aren't going to affect it at all. So it's kind of like saying you have 2x over 3x, which is really like saying you have 2 over 3. Are there any questions? It's approaching 2/3.
Would that number on the right be so big that you can't ignore it?
Plus infinity. I mean,
So basically nothing's big enough.
Right. Yeah, good question. Great question. All right, let's look at number 3. Again, we've got a degree on the top that's higher than the one on the bottom. You can follow that little table, or we can just sort of think about this. That 3, if you put in a humongous number, is that 3 really going to affect it? No, it's really not. So it's kind of like saying you have 5x squared over x, which is like saying you have 5x, and if you take infinity and you put it in place of that x, what do you have? Which is just kind of infinity, right? It's approaching infinity is what's happening here. Now, here's the thing. When we went through this stuff, did I leave one off? No, I'm okay, I think. I think I'll put them all in here. It's approaching infinity is what's happening. So it is approaching infinity, and that's your answer. Now, here's the thing. When we went through this the first time, I let you guys put either answer. You could put D and E, does not exist, or you could put infinity. Do you guys remember that kind of? Here's the thing. On an AP test, if it's multiple choice for this type of a question, one of your answer choices may say D and E, or one of the answer choices will say infinity. So you need to be prepared to answer it either way. You see what I'm saying? So just kind of know those are both sort of possible answers. You need to be ready for either one. So for today's purposes, none of your answers will be D and E. For today, for me today, on your assignment, I need positive or negative infinity if that's supposed to be the answer. Does that make sense? Okay. Everybody okay? Ocean, you okay? Okay. Just checking. Alrighty. Let's keep moving down. What if, let me ask you this though, What if this had said the limit as we're approaching negative infinity? Would that change it at all? You work through the same process and it's 5 times negative infinity, which means what's our answer? Negative infinity. Good. Okay?
But wouldn't both x's be negative?
Well, what would happen is, like, if you put it in right here, you would have negative infinity times negative infinity is positive infinity. So you'd have a positive divided by a negative, which is still a negative. Good question. I did, but she was just saying, what if I put it in there?
I know, when you cancel out.
And either way will work. The way Heather's talking about will work, or the way you're talking about will work. So don't stress. Don't get confused. You're on track. You're fine. I think you're okay. Yes, we canceled them out. Yes, it's just 5 times negative infinity. You are correct. You're good. No, 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 no. No, 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 no. Watch. You'd have negative times negative, so on top you'd have a positive divided by negative infinity. You see what I'm saying? Okay, just make sure you're with me. Number 4. You can plug in a bunch of stuff, but remember, really all this little stuff over here doesn't really matter. We're kind of just looking at these guys here. So we have 3x squared over 4x cubed. If you want to kind of reduce that thing down, we have 3, whoops, I don't even know why I wrote that, sorry, 3 over 4x. So if x is like some massively large number, what's happening with that fraction? What are we getting closer and closer and closer to? 0, because it's a tiny number over a really large number. And so because this is your notes, you might even want to write that down so you don't forget where you got that. Tiny over really big is going to equal 0. So we're approaching 0. Making sure, I'm sorry, I'm just checking my notes to make sure I've said everything I want to say. I don't want to skip over something.
2x wouldn't be like included 4x cubed.
Because it's the same, like it's, and if you're taking infinity to the 3rd power, then this infinity is not going to affect it that much. You know what I'm saying? I forgot to move that out of the way. I'm so sorry. If there's no reception over here, and that's why I usually put it in the captain's usually safe in there. Okay, number 5. We have 2 problems on number 5 because I kind of want you to look at this a couple of times. The first one we're approaching positive infinity. The second one we're approaching negative infinity. So when we look at this, there's like more than one way to kind of look at this. That radical kind of freaks me out. I don't know about you guys, but I'm looking at that going, I don't want to do that. I don't want to think that hard. So here's something you can do. You can say, okay, I've got 2x plus 1 over. I'm going to put that whole thing in parentheses and raise it to the half. Right? Because the square root is raised to the half. Same thing. If you have a power raised to a power, what do you do with those exponents? You multiply them. So I've got 2x plus 1 over x squared to the 1/2. Isn't that really just x to the 1st power? Because 2 times a half is 1, bless you. Minus x to the 1 times a half is a half, so I really have a radical x right there. And now you can do what we've been doing where we said, okay, these guys don't really matter. I'm just concerned with 2x over x, which is what? 2. It's approaching 2. Now here's the thing with this, if we're approaching negative infinity, and here's something to really think through. If you plug it in there, what happens when you square negative infinity? It becomes a positive. Is there any way that bottom part is ever going to be a negative anyway? No. That bottom piece is always going to be positive. And so the top, you're going to have 2 times infinity, which is going to wind up being a 2. Or the negative, thank you, I'm sorry. So we have negative 2. It's negative 2. Because we have, sorry, let me fix this. So we have, you have 2x over x is what we had, right? That's kind of what this was over here. But this, like, you know this is going to be positive. Even if you plug in that negative infinity, this has to be positive. Hang on, positive infinity is what it, positive infinity is on the bottom. The top, we have 2 times negative infinity. So those infinities cancel, and you're left with your, wait, why isn't it negative 2? Oh, because it's negative on top. Because it's negative on the top. So we still wind up with our negative 2. That's what happens. I didn't explain that very well, sorry.
Okay, so,
Do you guys kind of see what happened? Yes.
so you're using like the choice for x from the time that we kind of first deduced it, right?
Yeah, you can do that.
And so then when you bring it over, why don't you just put the negative infinity in both x's?
Because you know, it's because whenever we sort of got rid of all that, like back up here, it was being squared, and you can't forget that. You know what I'm saying? Good question. And it may be easier on both of these to just think about plugging in infinity into both of those, and that's a negative infinity. What you can't forget is that you're squaring it on the bottom, so you wind up with a positive. You can't forget that. You just can't. Special limit. The limit as we're approaching 0 for sine of x over x. Some sort of special. And an option that I haven't talked about this far, and I probably should. Actually, let's do that. Grab your graphing calculator. Because here's another way to focus on some of these things. You will not always be able to use a calculator, but you do have it, and I noticed that lately I haven't been using it at all with you guys. Hit your y equals button, and we're going to type this problem in. So we have 2x plus 1, in parentheses, divided by, is your calculator okay? Divided by the square root of x squared minus x. So we type the problem in. I'm going to go to second window. I'm going to set up my table so that for independent, it says ask. Because I want to plug in the numbers I want to plug in. Hit second graph to go to your table. And I'm going to type in numbers getting larger and larger and larger, like 100, enter, 1,000, enter, 10,000, enter, 100,000, 1,000,000. What are we getting close to? 2. It says that every single time. Let's do the same thing, but let's think about negative infinity. So I've got negative 100, negative 1,000, negative 10,000, negative 100,000, negative 1,000,000. And we're approaching negative 2. So you can always look in your calculator. Okay. This next one, and you could also graph things to kind of look at it. This graph, if you plugged it in, I think it kind of does this. It oscillates back and forth. It gets bigger, and then it gets tiny, tiny, tiny. So as you're nearing infinity, it's oscillating back and forth over that x-axis. It's getting super duper duper close to 0. Or you could kind of think this through. The sign of anything, isn't the sign of anything always somewhere between -1 and +1? It's always some sort of small number. So I have a small number over, if I keep plugging in infinity here, it's going to be a big number. When you've got a small number over a big number and it keeps you keep getting this big number bigger and bigger and bigger, we're getting close to 0. So that's another way to think about that one. Well, let's look at this one. Now I know that if I can make this one, did you find everybody? Did it go okay? Did anybody not do it?
There were 2 people who didn't do it, and then the ones with dots by their names, they already got collected.
Oh, perfect.
Okay. And
Okay.
then only Anderson.
Because they've already been collected, will you highlight them for me? So I
Okay,
don't
yeah.
forget. That'd be awesome. Thank you for doing that. I appreciate it. And then I'll walk you through all these notes here in a minute. And you can have my copy. What would be cool is if I could make this guy right here look like this one, then I'd kind of know something about it. Do you kind of... You guys remember how to do that? Do you remember that we could multiply by 2 over 2? which is perfectly legal because it's 1, all dressed up. And when we do that, we get the limit as x approaches infinity for 2 times sine of 2x over 2 times x. And now, this looks like this guy. And we know the limit as we approach infinity for that. It's 0. So I have 2 times 0, which is 0. Everybody okay? 7. Take negative infinity. You plug it in here. 1 over super huge sort of negative number. What are you going to get? Where's it? What's it approaching? Yeah. This number is getting tinier and tinier and tinier. And so if this is 0, what's the sign of 0? 0. So it's approaching 0. Are you okay so far? This guy over here, you can create common denominators and you can do all that. You can follow your degree rules, that's fine. Or you could sort of logically think this through. We can cancel the x's. You can't cancel the x's. These are 2 totally different terms. It doesn't work like that. I can't tell if he's kidding or not. If you put in a negative infinity here, what's this one getting really, really close to? It's approaching 0, because that fraction is getting tinier and tinier and tinier. Plus, if I put negative infinity here, what am I approaching? A really big negative, so it's approaching negative infinity, right? So 0 plus negative infinity would be negative infinity. But again, if you wanted to do common denominators, and I'm not going to take the time to do it, but if you wanted to, make yourself a note. If you did common denominators and put them together and la-di-da-di-da, you'd wind up with the limit as x approaches negative infinity for x over 3. If you put a negative infinity there, isn't it just going to be approaching negative infinity? Yes. So you can do it that way if you don't want to think it through. Backside. Lopitals rule. And I did check online. Some professors are saying Lopitals. I don't really know his name. It doesn't matter. Looks like hospital to me. But I guess the background on this guy, and I haven't done tons of research, is he's kind of like, and I don't know if you guys watch The Big Bang Theory, but he's kind of like Wallowitz in the fact that he hangs around with a lot of super geniuses, but he himself is not a genius, or at least they make him feel like he's not. But he wanted to be big and famous and cool and geeky, and so he paid a bunch of money to put his name on this rule that his friends came up with. So it's kind of funny that it's not even his rule. But anyway, here's what the rule says. If you get an indeterminate form, and this is going to make a lot more sense once we do one. If you get an indeterminate form being 0 over 0, infinity over infinity, or negative infinity over negative infinity, if you get something weird like that, do Lopitals' rule. It's not hard, and it's going to help you a ton. Here's what his rule says. You've got 2 functions, and we're finding the limit as we approach whatever. Let's say the top function is a 0, and for the bottom function you get a 0. And if what else is true is that the derivative of the top divided by the derivative of the bottom, if as we approach, I put 0, that should be a C, I'm sorry, typo. If you get some sort of number, what that's saying is the limit, that's a C. From the very beginning would also be L. Again, this rule is going to make sense once you do one. Yes?
Is the line like, where is this x equal to 0 and wait, let's see.
This is, wait, say that again.
One above.
Do you have x equals
Give x
0?
equals 0.
No, yeah, these are zeros.
Well, is x supposed to approach 0 or
Oh, crap. Yep, good job. Just have it. I get used to putting zeros there. Thank you, good catch. So on number 1, I know you're not supposed to plug a 0 in because it makes the bottom undefined. I get that. But you might kind of remember when we first started doing limits, we would try to plug in the number to just see if it would work. Do you guys kind of remember that? And some of them came up funky where you had a 0 over a 0. So if I take a 0 and plug it into just the top, what's the sign of 0? Over, what's the sign of the bottom? I mean, not the sign of the bottom. If you put in a 0, you get 0. I see an indeterminate form, so my brain's going, oh, Lopitals, this should not be a big deal. Here's what you're going to do next. Your next step is to do the limit as x approaches 0 for the derivatives. And because this is my notes, just this one time, I'm going to put this so I don't forget on my notes what I actually did next. So the limit as x approaches 0 for the derivative of just the top. Now, yes, I know that that's a quotient. You want to do quotient rule. We're not taking the derivative of this entire function. We are looking at this as a top function and a bottom function. There are two different functions. What's the derivative of just the top? Cosine of x. What's the derivative of the bottom? 1. Now plug in 0. What's the cosine of 0? 1. And what's 1 over 1? The answer to the derivative of the very beginning, or not the derivative, to the limit at the very beginning is 1. That's how you can find it. So let's do another one. This will make more sense the more we do, I promise. Take a 0, we plug it in. What is 2 times the sine of 0? Sine of 0 is 0, right? So I really have 2 times 0 here, minus the sine of 2 times 0, so sine of 0 is 0, right? On the top, I have the 0. On the bottom, I have 0 minus the sine of 0 is 0. Indeterminate form. My brain's going, okay, Lopitals, this is not a problem. So, I'm going to find the limit as x approaches 0. Please rewrite this part. I know you guys want to skip it. The limit as x approaches 0 for the derivative of the top over the derivative of the bottom. The derivative of 2 sine x is what? 2 cosine x. Minus, what's the derivative of sine of 2x? Cosine of 2x times 2. Thank you. Got to finish the chain. Over, what's the derivative of x? 1 minus, what's the derivative of sine of x? Now let's plug in 0 and see if it works. 2 times the cosine of 0. What is the cosine of 0? Whoops. I'm trying to trade colors and I just threw a pen at myself. Ah. Okay. 2 times 1 minus 2 times the cosine of 2 times 0. Cosine of 0 is, we just said 1. And then we have 1 minus cosine of 0, you said was 1. So, bummer, I got 0 over 0 again. What do you do when you get an indeterminate form? Lopitals, you just do it again.
Why?
Because this, for all we know, could have been our first problem. The very first question, and we would have done Lopitals. So we do Lopitals. So on the next line down, I'm going to have the limit as x approaches 0 for the derivative of the top over the derivative of the bottom.
Hold on, I have a question.
Yep, sorry.
So where it says 2 cosine 2x, cosine of x is 1. When you multiply that, wouldn't that be 2 and then 2 times 2 is 4?
No. Cosine of x, cosine of 0 is 1.
Alright.
So I have 2 times 1.
Okay, yeah, look at the next one.
Oh, did I do it wrong? 2 times 0 is 0. Cosine of 0 is 1.
So you multiply before you find the line.
Yes. Because it's cosine of this whole thing. Good question. Does that answer where you were? You good? Were you okay? Oh, you're stretching. Okay. Let's see the derivative of the top again. Derivative of 2 cosine x. What's that? Negative 2 sine x. Minus. Okay, derivative of. Okay, I could put a 2 here, but I know it's about to happen, so I'm just gonna hold that 2 in my mind right here. Derivative of cosine is negative sine, right? So I have negative sine of 2x. Don't forget to finish the chain. The derivative of 2x is 2, and I had this 2 already, so this is a 4 now. Let me say it again. The derivative of cosine of 2x is negative sine of 2x. So I changed this negative to a positive, and I have sine of 2x. I have to finish the chain. The derivative of 2x is 2, multiplied by the 2 that was already there, and I have a 4. Over. Derivative of 1 is 0. I've got a negative, so the opposite of whatever the derivative of cosine of x is. Derivative of cosine is negative sine x. Why am I writing positive sine x? Because it was a negative. Good. All right, let's plug in 0. Negative 2 times sine of 0. That whole term is what? 0. Plus 4 times sine of 2 times 0. That whole term is 0. And on the bottom, sine of 0 is? What do we do?
Stop.
Do it again!
Why?
Because you'll get the answer wrong. That's why. So we do it again. So I'm looking for the limit as x approaches 0. Notice I'm rewriting that every time because you're supposed to. It's a question. It's asking a question. Derivative of negative 2 sine x is what? Negative 2 cosine of x. Good. Plus, what's the derivative of 4 sine of 2x? Good. 8 cosine of 2x. Over. Good. Cosine of x. And notice you're out of space anyway to write, so don't you think you're probably about to get an answer? Like I kind of planned ahead for you?
Sure.
Yeah. So we take our 0 and we plug it in this time. We're hopeful we're going to get an answer. We have negative 2 times cosine of 0 is what? 1. So I have negative 2 times 1 right here. Plus, I have an 8 times cosine of 2 times 0. So cosine of 0 you just said was 1. On the bottom, cosine of 0 is 1. Hallelujah. On the top, I have a 6. On the bottom, I have a 1, and we have an answer. Now, here's the thing. Don't stress too bad. On the worksheet, I did ask Miss Zamor, because I haven't actually worked it myself yet, and she said that there are only 1 or 2 where you're going to have to do Lopitals more than once. So it's not like you're going to do this every time, and I don't think you have to do it more than 3 times. So you will get an answer eventually on those. Does that make sense? So don't stress. I'm not going to make you do Lopitals like 20 times. No. Nice try. I'm going to keep talking. Kevin, question?
Will there always be an answer to the
Sometimes it'll just spin in circles, but you will not have any that look like that.
So if it leaves you in circles, what do you say? Just doesn't exist?
Is it, you say circles?
I think you probably have to find it a different way. One of the ways that we used to use probably.
We're not going to have one.
No.
At first.
Nope. My point is make sure you know how to do Lopitals. It'll work. It'll work pretty much every time. Here we go. This little guy here, there are 3 methods, hence the 1, 2, and 3. One method. Plug it in. Sure, let's do that. Let's plug it in. So if we have infinity and we... Wait. Before you plug this thing in, rewrite it. On the top, you still have 4x squared minus 5x. On the bottom, put negative 3x squared plus 1. That's going to help most of you see that a little bit better. Right, we don't worry about the rest. Good. So we have 4x squared over negative 3x squared. Your x squareds cancel. Yep. And that's the same thing before when we had those rational functions and we would say, oh, the degrees match, so it's leading coefficient over leading coefficient. That's where the horizontal asymptote is. It's the exact same process. We're just thinking about it a little bit differently. So that was that way. Ocean wants us to plug it in. So if I've got, so if I plug it in, let me rewrite this thing first. If we plug it in, I've got 4 times super huge number over negative 3 times super huge number. I wind up with negative 4/3 still. I'm going to recover that little guy up. Say it again?
What's the difference between the first and second? Or is the first method where like kind of simplifying it?
First method, I'm just sort of simplifying it down. Yeah, the second one, I'm actually thinking about plugging in infinity, what it would do. Yeah, good question. What else did I want to mention? I think that there are actually 4 ways to kind of approach this when I think about it. Oh, the other way is, yeah, you could go to plug this in and you get indeterminate form, and then you could do Lopitals. You could do that. Do you want to?
No.
Yeah.
Anybody besides Ocean want to do that? No takers. Sorry, Ocean. I will let you do that. It's not very long, actually. It's only 2 steps. And then the last one is, you could do this if you wanted. I'm going to rewrite it. I would not do it this way, but some of you might need this. It's going to feel a little crazy. You could factor out
What?
an x squared. I didn't say you're going to pick it. I'm just saying this is an option. So that you wind up with 4 minus, and if you're taking out an x squared, you wind up with x to the negative 1, which shoves it to the bottom. I know. It's pretty, right? And then if we take out x squared down here, then I've got negative 3 plus 1 on the bottom. Oh, wait. No, we take out an x squared. Sorry. So it's 1 over x squared. My bad.
Is it supposed to be limit approaching 0, or is it still?
Oh, shoot. See, I told you that habit gets me every time. Thank you, Tanner. Goodness gracious, that's infinity. Sorry, friends. That was the worst habit ever. So then our x squareds cancel, and then you can kind of think it through. I've got 4 minus 5 over massively huge number. So this number here is basically 0. It's super tiny. And then I have negative 3 plus 1 over massively huge number. So it's that one is getting really close to 0. So it looks like I've got 4 over negative 3. That is one way to do that one. Okay. That was a lot, but I think we're good. Here's your assignment. Page 205. Page 205. 4 through 40 every 4. That's 10 questions. You can do that. And then I've got a little Lopitals worksheet for you. Due Monday. Whoops.